In this video, we'll talk about the factor and remainder theorem and how we can use them to solve for x-intercepts of polynomial functions. So let's dive right in. Let's talk about the factor and remainder theorem. So the idea is if x plus a is a factor of f of x, then x equal to negative a is a root, or an x-intercept, or a zero of f of x. And that might seem a little strange at first, but it all ties back to the idea of zero product rule, and we see it all the time with quadratics. If we have x plus 1 times x plus 2 equals 0, well then x has to equal negative 1, or x has to equal negative 2. Basically all we're saying is that, okay, if we know this is a factor, then we know the opposite of it is a root. And this theorem actually is an if and only if statement. It goes both ways. If I know the root, if I know x equal negative 2 is a root, I know that x plus 2 is a factor for my function. And this is useful to us because if we know a factor, then we can do some division and work it down to a lesser degree polynomial. And then we might be able to factor using our knowledge of quadratics. So let's apply this to an example. Let's say we know that x equal to negative 1 is a root of f of x, where f of x is equal to x cubed plus 6x plus 11x plus 6, and we want to find all the other roots. Well, this x equal negative 1 being a root tells me x plus 1 goes evenly into f of x. So I'm going to do some long division now. So x plus 1 into x cubed plus 6x plus 11x plus 6. Again, we're going to look at leading terms. Ask ourselves, what times x makes x cubed? Well, x squared. So we get x cubed plus x squared. We're going to subtract that off. And then we get, looks like 5x squared. Oh, forgive me, there should be a little 6x squared up there. So, if we're looking at the next term after we bring down our 11x, we're going to look at x and 5x squared. How I get there would be multiplying by a 5x. So we're going to have 5x multiplied to 5x times the plus 1. We get plus 5x. Again, we subtract, and that would leave us with, looks to be 6x. We bring down our 6, and then we can, again, look at our leading terms. We're going to look at the x, we're going to look at the 6x, and then we're going to multiply by 6. So we get 6x plus 6. We subtract, we get 0. It worked out. So that means we do indeed have a root of negative 1. X plus 1 is a factor of our original expression. So this would tell me f of x can now be written as x plus 1 in parentheses times x squared plus 5x plus 6. That would be, for all intents and purposes, our broken down cubic function. We've factored it to a linear expression times a quadratic expression. So now I'm going to look at this, the quadratic expression. We have all kinds of tricks to break down quadratics, and in this case, I think this one factors. I'm looking at the factors of 2 that add to 5, or factors of 6 that add to 5, which would be 2 and 3. So we have x plus 2 and x plus 3. And I'll just keep the x plus 1 down here for the ride. Now, if we're looking for zeros, so when f of x is 0, we can then use zero product rule. One of these three things must be equal to 0. That much hasn't changed. So this would tell me either x equal negative 1, x equal negative 2, or x equal negative 3. Now, since we're talking about roots and x-intercepts, we can say I have roots where x equal negative 1, and x equal negative 2, and x equal negative 3. And that's how we can use long division and other roots to find roots that we may not know. And this is useful because if you graph a function in software, sometimes you get one root that's very, very easy to see. Then the others are decimals, very difficult to discern what they are. We can use this mentality or this method to solve for them.